You have a specific question about it, or you just want to see it worked out?
Yeah, like I guess I just kind of thought about it like a piece series.
Yeah, um, it kind of is. So you got to be careful about ones like this, and just the way you're thinking about it. So there are two different ways. Well, I guess there's many different ways to solve one like this. P series thing would definitely kind of work. um, the problem with that has to do with the difference between something converging absolutely versus something converging conditionally. Like we could just look at the sum as if this was not an alternating series, right? If it was just 1 over the square root n. Um, by the p series, whoop, that's not where I wanted that to go. By p series, this diverges, right? Because this would have an exponent of 1/2, and because that's the p in the p series, and that's less than 1, diverges, which is perfectly fine. The problem with thinking about it that way, it comes back to this one up top here, when you have the alternating series. Just because the absolute value diverges does not mean that the original series diverges. And just because the original series diverges does not mean that the absolute value series diverges. But they do have a relationship. If this one converged, then this one would automatically converge. But we don't have that. So we're going to have to do alternating series. And then by the alternating series test, there's 3 different things that you have to worry about. The first one is you have to make sure that your sequence without the alternating part is all positive. You have to make sure that your sequence values are non-increasing. And then you also have to make sure that the sequence values itself goes to 0. And hopefully all of these you can just kind of look at. My formatting's all funny, but hopefully you can just look at it and tell that this is going to be true. For this example, the sequence values, those use of n's, is going to be just the 1 over square root n part without the alternating part. These are all positive. These are non-increasing. As my n gets bigger and bigger, my values get smaller and smaller. And then if I take n to go to infinity, it does go to 0. So because all 3 of these things are satisfied, then the series converges.
Gotcha. Okay.
And we
Yeah, I
can,
was kind of just thinking over the test and just like being like, yeah, it's a piece series. But yeah, I see what you're saying.
yeah. But because we did look at this part, that means we can say a little bit more about this. It doesn't just converge. In fact, it conditionally converges. Right? Because the alternating series converges, but the absolute value series diverges. So yeah, it's a little bit nuanced, and you just have to be careful with those definitions, and when one converges, what does it say about the other, and vice versa. So yeah, I hope that helps.
Yeah, no, definitely. Thank you.
Mm-hmm.
Could you sort of rehash what it means to converge conditionally versus what it means to converge absolutely?
Yeah. So if we have just a series, whatever that series is, a sub n. So it could either converge or it could diverge. So let's say this one converges. Okay. Then we also have the absolute value series. So this would just be the series of only the positive values of the same series, but just positive numbers the whole time. If this converges, then we can say that the original series converges absolutely. Okay. So this says that we have absolute convergence. Because not only does the series itself converge, but the absolute value series converges. On the other hand, if you have that the original series converges, oops, but then you take the absolute value, just kind of like in that example we saw of above, if they were all positive and this diverges, that says that the original series converges conditionally. I have my stuff kind of backwards, but if the original series converges and the absolute value converges, you have absolute convergence. If the original series converges, but the absolute value diverges, that means that your original series converges conditionally.
Okay, thank you.
You're welcome. One nice thing about this is that if you have this, like if you know that your absolute value converges, you automatically get that the original series converges. So an example of that, let's go down to the next page. If you had this series, so let's say you have the alternating series over n to the fourth, like that. We don't even have to do the alternating series test here. I already know that this converges since the absolute value series just 1 over n to the fourth converges. Does that make sense why we can say that in that direction?
Yeah, I think so.
Okay. I've lost my chat. If anybody types in chat, just let me know. Is there any other questions from the practice stuff or the other practice test I sent out or the homeworks?
I just have a quick clarifying question on interval convergence.
Okay.
Like with testing the endpoints, I just want to make sure I'm like thinking about this right. So once you get your endpoints, you plug them into where there was an x value in your power series.
Yes.
Then once you simplify it down, whatever's left over, you should be able to decide whether it converges or diverges, and that basically tells you what your inequality symbol is.
Yeah, that's the gist of it. So when you find your interval convergence using like the ratio test, the ratio test is not going to help you with the endpoints. So you have to plug those endpoints back into the original series and use something else to see if they converge or not. And then, yeah, if they do converge, that's when you're going to have the or equal to inequalities, and if not, then just the strict less than.
Thank you.
You're welcome. You want to go through an example of that?
Sure, go for it.
This one looks big, but we can do this one. So let's copy it down here. So it was x minus 8 to the n, all divided by n cubed times 7 to the n. Okay, great. And the question is just asking us to find the interval of convergence. So first things first, the ratio test, which says to do the limit of the n plus 1 term divided by the nth term. Usually I just write out the n plus 1 term just as is. Cool. And then multiply that by the reciprocal of the nth term, just to save me some time of having to write it out 2 separate ways. Awesome. So the n plus 1 term, just replacing all of my n's with n plus 1's. And then we're dividing that by the nth term, which is the same thing as multiplying by the reciprocal of the nth term. And now it's just all about using different tricks. Because we have mostly exponents here, we're just going to break that down using the product rule of exponents. X minus 8 to the n plus 1 is the same thing as x minus 8 to the n. times just a single x minus 8 to the 1. In the denominator there, that n plus 1 cubed we can't really do anything with, but the 7 to the n we can split up to be 7 to the n times 7. Trying to make it look as neat as possible. Oh, forgot my extra 7. Alright, so this is just this first fraction kind of simplified down a little bit. X minus 8 to the n plus 1 is x minus 8 to the n times x minus 8. N plus 1 cubed, there's not really anything that we can do there, except for multiplying it all out, which I do not feel like doing. But the 7 to the n plus 1, we can split up to be 7 to the n times 7. My other fraction here, I'm just going to leave as is. I'm not going to mess around with that. And the reason for that is because a lot of this stuff should cancel out. I now have, let's see if I can, oh, I found my chat. Okay, great. So this x minus 8 to the n cancels out with this x minus 8 to the n. This 7 to the n is going to cancel out with that 7 to the n. So what we're left with is still the limit, still the absolute value. We're going to have an x minus 8 and an n cubed up top. And in the denominator, the only thing it looks like I have is that n plus 1 cubed. Okay, so I know this next part is a little bit weird, and technically it's L'Hopital's rule that's going on, but we've talked about this a little bit before, just thinking about it as the horizontal asymptote. If you were to multiply out the denominator here, the leading term would be an n cubed. So we have an n cubed up top and an n cubed on the bottom. Whenever you take the limit as n goes to infinity, that's going to approach just the quotient of those coefficients. My coefficient on top is x minus 8, and my coefficient on the bottom is just 1, so this approaches the absolute value of x minus 8. That, remember, is our p-value, and we want that to be less than 1 so that my series converges. Whenever you have an absolute value is less than 1, that's when you squeeze it in between the negative and the positive. And then for us, we can just add 8 on both sides. Okay, great. Get those lines out of the way. Okay, so is everybody okay with that part? Is there any questions about this awful mess first before we do the endpoints? All right, I'm assuming we're good. So then, yeah, now we need to test the endpoints. So we'll start off with just the first endpoint there, x equals 7. So what you want to do is you want to take this x equals 7 and plug it all the way back into the original series. So we're going to get the series. If I plug 7 in for this x, 7 minus 8 is negative 1. That's to the n. And that's still divided by that, n cubed 7 to the n. Now we just need to decide if this converges or diverges. We cannot use the ratio test, it's just not going to work, so we have to use something else. It is an alternating series, which is kind of nice, so we'll try that. So with the alternating series, there's the 3 different things you have to worry about. The first thing here we need to worry about is that my use of n's, which is 1 over n cubed 7 to the n, they're always positive. That should be easy to see that that's true. All right, as long as n's are positive, this comes out to be positive. What might be a little bit hard to decide is if this is non-increasing, but maybe it's not that hard. It's true as well. If I keep making my n's bigger and bigger and bigger, it's just going to make the denominator bigger and bigger, which makes the whole thing get smaller and smaller. The last thing we have to decide is that my use of n's go to 0. Same thing, right? If my n's go to infinity, this whole thing just goes to 0. So this is also true, which means that it does converge. So when my end point is 7, this is going to change into a less than or equal to now. We also need to try the other endpoint when x is 9. So plugging that one in, we're going to get the series of just 1 divided by n cubed 7 to the n. Okay, and now we need to do a test to see if this converges. This one's going to be a little bit weird. So we have this 1 over n cubed, and we have this 7 to the n, and trying to decide whether this converges or not. We cannot do the integral test because it would be very difficult to integrate this. And other than that, we're kind of out of tests at that point. I think the limit comparison test is about all that we can really do now to see if this is going to work. So let's try. I don't know if this is going to work yet or not. The limit comparison test. And what we want to compare this to is let's try comparing this maybe to the series 1 over 7 to the n. Great. The reason I'm comparing it to that is because 7 to the n blows up to infinity a whole heck of a lot faster than n cubed blows up to infinity. So this is going to be kind of the dominating term of my series here. We also should, it's easy to kind of see, I hope anyway, that this converges. That we could just do the integral test with, but I don't know. It should be easy enough just to see that that is definitely going to converge just based on how big that denominator goes to 0. And because that converges, then by the comparison test, we also get that the other one converges. Since we get that 1 over n cubed 7 to the n is always going to be less than 1 over 7 to the n. I said limit comparison test, but I think this is just the regular comparison test, not the limit one. Just the regular comparison test for this. The point, though, is that when x equals to 9, we also get convergence. So therefore, my interval should be 7 less than or equal to x less than or equal to 9. I hope anyway. Let's see what the thing says. Way off. Oh no, what did I do?
Forgot the 7. Way back at the...
Oh, you're right. Way back here, there was supposed to be a 7. Oh no. Alright, just do all of this stuff, but pretend that there was a 7 involved. Oh, that sucks. We didn't even try the right endpoints then. All of this was for nothing. Alright, so instead try 1 and 15. They should be a lot easier to try. Like if I'll just do these real quick then, since I messed it up so bad. If I do plug 1 into it, I get negative 7 to the n divided by n cubed 7 to the n. But then those 7 to the n's cancel out. And this is really just the sum of negative 1 to the n over n cubed. That definitely converges. That's just a p-series thing that we were talking about before. If I try the other one, if I try to plug in 15 in it instead, that's going to give me 7 to the n up top divided by the n cubed, 7 to the n. So then the 7 to the n's cancel, and we just get the sum of 1 over n cubed, which also converges by p-series stuff. All right. So then that leaves us with the final answer there. 1 less than or equal to x less than or equal to 15. All right, sorry I messed it up. I forgot my 7. Don't forget your 7 on your test. But that's the gist of it. So I hope that helped, even though I messed it up so bad. Any other questions that I can hopefully not mess up next time? From either the practice test or from the practice stuff?
We do, I think it's the practice test, and
Find the Maclaurin series for the given function without using substitution. Use substitution to check your work. Yeah. So e to the negative 7x. Okay. So whether you're doing Taylor series or Maclaurin series, they're going to give you a function. So here they give us the function e to the negative 7x. You're also going to want to know the formula for it. So just real quick, writing down the formula for the Maclaurin series, it's going to be the kth derivative at 0 divided by k factorial. Oops, that is not what I wanted to do. And then it's just x to the k, right? So usually there would be these a values in here. This would be the kth derivative at a, and then this would be x minus a to the k. But the Maclaurin series just has your a to be 0. The hardest part is finding out what this derivative needs to be as like a just to the k, a generic one. So usually what I do is I just do a few different ones until I get a pattern going. So just starting off when k is 0, that's going to be the original function itself, e to the negative 7, not k, sorry, e to the negative 7x. But I don't really care what that is. I want to know what that value is when I plug 0 into it. And if I plug 0 in for the exponent, I'm just going to get 1. Then I would take a derivative. Taking the derivative of e to the negative 7x gives us negative 7e to the negative 7x. But again, I don't really care about that. I want to know what happens when I plug 0 into it, and that spits out negative 7. Maybe a couple more. Take the derivative again, I get 49 e to the negative 7x. Plugging 0 into that gives me 49. Okay, so hopefully you can just kind of visualize what the pattern is going to be. It looks like I alternate positive, negative, and it also looks like I'm just multiplying by 7 every single time. So that means I can write out what my kth derivative would be at 0. It looks like it's going to alternate, so there's going to be a negative 1 to the n factor in there. And then other than that, it looks like there's just going to be a 7 to the n. So the first one's 7 to the 0, 7 to the 1, 7 squared, and so on and so forth. And I put n's here, and I meant to put k's. I think I did that in the videos a lot too, where I alternated n's and k's by accident. Alright, and then that's pretty much all you have to do. Now you just plug that into the formula. So this says that my Maclaurin series is going to be the kth derivative at 0, which is this, negative 1 to the k, 7 to the k, divided by that k factorial times x to the k. If all they're asking you to do is to find the Maclaurin series, that is the Maclaurin series. You can't simplify that down anymore. Sometimes they're going to ask you for the Taylor polynomial, or they're going to ask you for the first few terms of the series. So that's where you'd want to actually plug these values in. So notice here that the answer I got, even though I put k's in it and they have n's, it's still the same thing, right? That negative 1 to the n, the 7 to the n, the x to the n, divided by the n factorial.
What did it mean when it said without using substitution?
That's a good question. I really don't know. I was thinking about that as I was talking.
I was like, I don't want to do that, but I didn't know what it was, so I didn't know how to not do it. So.
I think that there's an alternative way of doing the Taylor series and the Maclaurin series besides the way that we're doing it that sometimes can be easier with the substitution idea. But I've never seen it before, and I would never ask it before. This is not my test. This was just somebody else's test that I stole. But I don't know why it says that. I don't really know what that is. I'm going to Google it, though. Tricks with it's just a trick. I don't know. I don't feel like reading through all that right now, but It's just a trick. Don't use any special tricks. Oh, there we go. That's why. So the substitution method is basically a U substitution, but for Taylor series. So what you could have done with this is you could have let U equal to that negative 7x up top, and then just done the normal Taylor series for e to the U. That's a really common one, and you could probably just Google that one and figure out what that one is. E to the U would just be x to the U, or sorry, x to the k divided by k factorial. Like just like that. So then there's a special trick to do with the U substitution into a Taylor series. Anyway, I didn't show it to you, so don't do it. Or don't try it.
Sounds good.
Yeah.
And also number 12 on the same one.
Yeah, also something that I wouldn't ask you to do. But just to talk through it, the whole point of Taylor series is that it allows us to do a lot of calculus that we wouldn't be able to do normally. This is something that's impossible to find the limit of just the normal way, like with L'Hopital's rule and other ways. But if you write this out using the Taylor series, there's a very easy way to find the limit using Taylor series. So, I mean, you're not going to see a question like that, so don't worry about it too much. Any other questions you guys want to look at or talk about?
Number 13 on that one.
Is that the bonus one?
Yeah.
Yeah. Okay. Yeah, so this may be something that you see. I think I did talk about this a little bit with the remainder theorem. So the polynomial blank is used to approximate this, 1 plus x to the fifth on this interval. Use the remainder estimation theorem to estimate the absolute maximum absolute error. So with the Taylor series, there's just a nice little formula for the remainder at the end. Also remember that we looked at remainder stuff with the integral tests as well. It's very, very similar. I would just have to look up the formula here just real quick. Let me pull it up. I think it's in section 9. One thing that I would recommend to all of you, like right before you take the test, is to write out all of the different formulas and tests and theorems that you think are important, just to have them all in one nice space. That way you don't have to spend a lot of time searching through your material and notes to find stuff. I don't know if I'm going to get the book to pop up here. Usually when I'm on the WebEx thing, my internet slows down so much that I can't get websites to work properly. Maybe Googling it. Taylor series remainder theorem. Yep, here it is. Yeah, so the remainder theorem is just the n plus 1 term. That's the gist of it anyway. So if you ever need to bound it, this is the formula. So it's going to be the absolute value of the remainder is less than or equal to this m value, where the m value is the upper bound of the n plus 1 derivative. All right, so going back to the question that we had here, this was the polynomial, and we're using just this polynomial to approximate this function, which means that we only went up to the second k value or n value. So we're going to use the third value to do this, which means to take the third derivative. So we have this f of x is equal to, oh, Word is crashing on me. Come on back, Word. You can do it. it might be dead. Come on, Word. Everybody cross your fingers. And your toes. All right, Word is back. All right, so yeah, if we're given this function, I think it was 1 plus x to the 5th, we need to take the third derivative of it. So it's just first derivative would be bringing the 5 down, leaving the inside alone, and then taking 1 away. Derivative of the inside is just 1, so that's nothing. Second derivative, same kind of thing, bringing down the 4, taking 1 away. But finally the one that we need, which is the third derivative at x, and that's going to be bringing down the 3, taking 1 away from the exponent. Okay, now we don't need this as is. What we really need is going to be our centering point plugged into this third derivative. And it's not quite obvious what the centering point is necessarily just by looking at it. That's coming from these coefficients out in front. So here we have the coefficient of 1. The only way to make this to have a coefficient of 1 is if x is 0. Same thing here. This has a coefficient of 5. The only way to make this one have a coefficient of 5 is if my x is 0. So it looks like we have a Maclaurin series here where x is 0. So now we need to plug 0 into the third derivative and we get 60. That's going to be the m from that formula. So if we're bounding our remainder here, where that needs to be less than or equal to that m, and then what was the formula exactly? X minus a to the n plus 1 over n plus 1 factorial. Okay, so x minus a to the n plus 1 divided by that n plus 1 factorial. So plugging in what we have, we just found out that that m is going to be 60. That's the upper bound of the third derivative. And then x minus a is really x minus 0. So this is just going to be x to the n plus 1. And then that's going to be divided by n plus 1 factorial. Remember that the n... oh, I guess we can go ahead and plug the n in for this because we're on the third derivative. So we're at... we stopped at the second n value. So this needs to be 3. And then we're dividing this by 3 factorial. And 3 factorial is just 6, so it looks like we get 10x cubed. Okay, so going back to the question, the polynomial blank is used to approximate on the interval blank. Use the remainder estimation theorem to estimate the maximum absolute error. At this point, you would just plug 0.01 in for this x, and then that would give you the maximum error. So whatever 10 times 0.01 cubed is, should be the error. So let's see if that matches something down here. Well, kind of. Like it's to the -5th power here. And I think if you were to multiply this all out, you would get a -5th in the end. I also feel like I did my 60 wrong. Well, anyway, that's how I would do it, right? So you stopped here at the second term of your Taylor polynomial. You have to use the third term of the Taylor polynomial to bound your Taylor series. So first finding the third derivative's constant value, which is the 60. That's going to be the upper bound here. So that's going to be the m. And then the a is 0, since that's where we have our Taylor series centered. So this is just going to be x to the n plus 1. But since we stopped at 2, my n is 2, so this is going to be the third. So x cubed, and that's divided by the third n plus 1, 3 factorial. All right, so I hope that helps on a question like this. We're using that remainder estimation theorem. It all comes from this formula. So does that make sense? Is there any questions about setting that one up?
Yeah, that's good. Thank you.
Okay, cool. Okay, any other homework questions or test questions or test prep questions?
Can we do number 10 on the same test we've been working on?
Yeah, number 10. Use power series operations to find the Taylor series at x equals 0 for this. Yeah, let me copy down the function. F of x equals x to the fourth. Okay, so this just says to find the Taylor series at x equals 0. In other words, we're finding the Maclaurin series again. So just to write out the formula for that, it's the kth derivative at 0 divided by, wrong button again, divided by the k factorial, and then that's times x to the k. So we just have to find that derivative sequence again. So just writing it all out like we did last time, leaving the value alone. We don't really care about that, but we do care about plugging in the point 0 for this example into that. And if I plug 0 into that, it looks like I just get 0. Then I would take the first derivative. Unfortunately, that looks kind of ugly. I would do a quotient rule here. So it's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom, all divided by the bottom squared. Is that big enough? Can you guys see that all right? Maybe I can make it a little bit bigger. There, is that better? Cool. And then just to simplify this down a little bit, multiplying it all together, we get still a fraction, 4x cubed minus 20x to the 24, sorry, x to the fourth plus 6x to the fourth, all divided by some stuff down here. And then if we can simplify that down a little bit more just by combining the like terms in the numerator. So minus 18x to the fourth up top. It's not going to matter too much anyway for this one, because if I plug 0 into this, I'm still just going to get 0. So we still don't have any terms yet. I have to keep going. The next one that I would do would be the second derivative, which is going to be even grosser. So if I take the second derivative here, it's going to be the top, or sorry, not the top, the bottom, 1 minus 6x squared times the derivative of the top, 12x squared minus a really big number, 72x to the third, minus the top times the derivative of the bottom. All divided by the bottom square. All right, it's just getting ugly at this point. I'm pretty sure that if it plugs 0 into this, I'm still going to be getting 0. So we would just have to keep going until we eventually got a number. And I don't really want to do that over and over and over again. Let's see what the answer is and see if how far we would have to go. This was number 10, right? Yeah, x to the fourth over, so it comes out to be that. Yeah, so unfortunately, the method that I showed you guys of how to find the Taylor series, the derivatives just get so awful that it would take you forever to actually get down to a value that has a coefficient out in front of it. So that's why there are those other ways of finding the Taylor series, like with the substitution method, and then there's a couple other methods as well. I think that's what this example is trying to get you to do. And it looks like I should have done a little bit better with reading through these. Because it's just too hard for the way that I showed you guys how to find Taylor series. It's too much trouble to go through these derivatives to find something easy enough to solve for. You're not going to have anything like this, I promise you, on the test. Your stuff is going to be more like the last example we did with just the e to the negative 7x kind of thing. And it's not that it's impossible, it's just that these derivatives are just too ugly to keep playing around with. And I'd rather not waste your guys' time just doing these derivatives over and over again. So I know that doesn't help too much with that question. It's just not something that I would ask you guys to do. But that's how you would do it. So I guess you can throw out 10. And there was another one we could throw out too, wasn't it? That I did? Oh, 12. 10 and 12, you'll definitely aren't going to see anything quite that complicated. Definitely not 12, and 10 is pushing it just because the derivatives are too hard. So is that all right? Does that make sense? Is there any other questions that you guys want to look at from these series and sequences before the test? Do we all feel okay about all these other tests, the geometric series, nth term, integral test, comparison test, ratio test, alternating series test?
Can we do number 5 on that one? Because it's a
Ratio test?
Yes, give me number 5.
Yeah, we can do that. So for this one, just the sum of 8 to the n divided by the n factorial. Alright, so if they're just asking you to do the ratio test for something like this, remember that the ratio test all has to do with that limit. So it's the limit of the absolute value of the n plus 1 term divided by the nth term. So for us, it's going to be the limit of, I'm just going to go ahead and do the n plus 1 term and then multiplied by the reciprocal of the nth term. So a to the n plus 1 divided by that n plus 1 factorial. That multiplied by the reciprocal of the nth term, which would be the n factorial divided by 8 to the n. So I would write it like that. And then there's some tricks to this one, and the tricks all have to do with the exponent rule and then the factorial definition that we have. So this 8 to the n plus 1, I would rewrite that as 8 to the n just times 8. This n plus 1 factorial, I would rewrite as n plus 1 times n factorial. The other fraction I would just leave alone. All right, so again, 8 to the n plus 1, we could separate out to be an 8 to the n times just an 8 to the 1. N plus 1 factorial, we would rewrite as n plus 1 times n minus 1 times n minus 2, like all the way down. But another way of writing that would be the n plus 1 and then just times n factorial, the rest of the numbers down. And then the reason we write it like that is that way this n factorial cancels out with this n factorial, and this 8 to the n cancels out with that 8 to the n. Which means that we end up with just the limit. Oop, that's not going to work. Come down to the next line. The limit of the absolute value, it looks like I only have an 8 on top, and I have an n plus 1 on the bottom. And then as n goes to infinity, my denominator blows up, which makes this whole sequence just go to 0. And then remember that this is my p-value for the ratio test. With the ratio test, there was 3 different outcomes. The first outcome is that if p is less than 1, your series converges absolutely. which is what we have here. So because my p-value ended up being less than 1, this series, 8 to the n over n factorial, converges absolutely. If this p-value came out to be greater than 1, then this would diverge, and if it came out to be equal to 1, then the test would just be inconclusive and you'd have to try something different. So does that make sense? Is there any questions about that one? Did anybody else have any other questions from the homeworks, from the practice tests? Anything to help prepare before the test next week? Well, if there's not any other questions that we can get out of here. So last call. Anything else? Any other questions from this practice test? From the the other one got deleted on me when Word crashed. But from the practice stuff, questions? Anything at all?
You said the test is open notes, correct?
It is, yeah.
Okay, thanks.
Yep. It's just that there's a time limit. I think the time limit is 3 hours on it, so just make sure you have everything like in front of you. Don't waste a lot of time rummaging through your notes. See if I can see how long it is exactly. Yeah, 3 hours to take the test. But yeah, you can use your book, you can use your notes. Just don't want you guys using each other or other people.
How many questions is it?
It is... I don't know. Let me see. I don't think it's that many. $20 questions.
Okay. Cool.
Yep. Any other questions before we go? Everybody's good? Most of it. Okay. Well, if you do have any other questions, just email me. I can try to make a video about specific questions. If you have specific questions that you want me to look at.
I saw it now. It was the, no, I wouldn't. Never mind. It was one that did something funky with the testing out where it ended up dropping the number down, but I can't remember.
Yeah, I don't know. I'm not sure which one you mean.
I don't have anything.
All right. Well, if you find it later, just email and let me know, and I'll try and work it out for you. All right. Well, let's get out of here. Of course, the test is next week, so I don't know how beneficial it would be to do these meetings next week. However, the week after that, I've gone ahead and start putting up Chapter 11 videos and Chapter 11 homeworks. So make sure, as soon as you're done with that test, you just go ahead and jump right away into the Chapter 11 stuff to work that out. Chapter 11 is the last chapter that we're going to be doing, and we have a few weeks to get through it, so there's plenty of time. So take your time with it and don't rush through it unless you really want to. Good luck on the test. I don't really know much else to say about the test itself. I think I gave all the pointers that I can think of. I know the test is well-rounded. It's about the same amount of questions coming from each section. So go back and look at the old stuff in Chapter 10 as well as the Taylor series, the McLaurin series stuff at the end, and you'll do fine. Also, don't forget that in Moodle, if you want, you can upload your scratch paper from the test, and I'll give partial credit just like I do for normal in-class tests. So make sure you have something to upload your scratch paper right after you take the test for partial credit. All right. Other than that, I'm leaving. So bye.